Okay, I'm not really sure what happened previously, but that's the first time my computer has ever done that. It just locked up on me. So hopefully that's not a sign of things to come. So I've rebooted and started back, and I'm back into R. I've set the working directory, attached the data, and so on and so forth. Now, where we were previously is we were getting ready to calculate the p-value, and we had some calculations where our test statistic was 0.301, and since we're conducting a two-tailed test, we're interested in the cumulative, the combined area in the two tails. Now, the way that the PT function works is it gives me whatever value I put in, it gives me the area below. So I don't want to put in the 0.301 because that's going to give me the area here. So it should be pretty clear that if I put in negative 0.301, it's going to give me this area multiplied by 2 to account for this, and I'll get my p-value. So let's jump over to R and make those calculations. Let's see, negative 0.301, okay. So use the PT function and go negative 0.301. And our degrees of freedom were nasty. I remember that, 19.532. Thankfully, I wrote that down. So our area in the left tail is 0.38329. So I need to multiply that by 2, and I should have done that when I did my calculations. 3833, that should be close enough. So guys, our p-value is 0.77. Now let's scoot back over here to the blackboard, green board, whatever that color that thing is. So anyway, let's kind of summarize what we have going on here. Our p-value is 0.77. So again, just kind of catch you, get caught up. We are testing that the mean difference of males minus females is equal to 0. And we're testing that against the mean difference for males minus mean difference for females is not equal to 0. And we're testing at alpha 0.05. Our calculations show that our test statistic is 0.301. And our p-value is 0.776, I do believe. I don't want to have that wrong. Let me just go over here and double check. 0.767, okay. So again, clearly this is greater than or equal to our alpha. So our decision here is going to be fail to reject H sub O. Now the video that I put up previously, I told you, and I call it stupid statistics because it would be, if we just examined the difference in sample means, it would be easy to conclude, and be completely wrong, that the average for males was higher than females. But considering we have natural variation, we have to build that into our final decision. And let the underlying probability distribution take its shape and make your calculations based on the fact that samples vary from sample to sample. So everything accounted for, we would fail to reject the null. Now the next thing you'd probably want to do is calculate a 95% confidence interval. And guys, confidence intervals in general always I'll tell you what, let me back up. I don't like the way I did that. What we would do next in all cases, and again, think about it, I'm trying to build for bigger, better stuff here. So let's keep it appropriate here. So what we would do next is calculate a 1 minus alpha percent confidence interval. Alpha is almost always going to be 5% or 0.05. So guys, what we would do here is calculate okay, a 95% confidence interval. Any confidence interval, regardless of whether we get into ANOVA, we get into regression, which will be the focus of the class. Consists of 3 parts. The part that goes here is your point estimate. So if we were constructing a confidence interval for mu, then we would put x bar there. If we were constructing a confidence interval for a population proportion, then we would put the sample proportion. Guys, in this case, we are trying to estimate the difference between that should be an F, but it's an ugly one, the mean difference between males and females. So guys, clearly, what should go in this part? I don't know why, but that's for some reason I just love working that eraser. It should go here. Alright, so we've got one of the 3 pieces of the puzzle. Let's go over to the very last. What will always go here will be the standard error. And just to catch you up, this part over here is called the margin of error. So one important component of the standard error, one important part of the margin of error is the standard error. Well, gang, in this problem, we have seen that the standard error is the square root of S1 squared over N1 plus S2 squared over N2. Now, the only thing we have missing is the critical value of our distribution. We saw earlier that the t distribution is the closest thing we can get to the underlying probability distribution. And this needs to be with degrees of freedom equal to 19.532. Now, to find this part right here, what we're ultimately doing is this. We are essentially saying in this distribution, the t distribution with degrees of freedom 19.532, between what 2 values does the middle 95% of our distribution fall? Well, gang, that's going to be really easy to do too, because all we have to do is go to R and use the QT function. So if I do QT 0.025, remember QT finds a score from the distribution given a particular characteristic. This characteristic that we want is 2.5% below with the degrees of freedom 19.532. So negative 2.089 will be the left bound. and obviously positive 2.089. Well, I don't know about obviously, but hopefully it becomes obvious, is the right bound. So gang, this tells us that our T critical for the degrees of freedom 19.532 is plus or minus 2.089, yeah. So gang, in terms of making our confidence interval, we're going to take the sample mean difference. So this is going to be quite a bit to write here. So this is going to be 60.72 minus 57.92 plus or minus stuff. All right. Now, when all the smoke clears, this should be, let me enter this in the calculator. And it looks like the left bound is negative 16.63. And the right bound is 22.223. I'm pretty sure that's right. I did it very quickly. Hope I didn't make a typo. All right, gang. Important point here. Ultimately, what are we trying to do? We're trying to use this difference to estimate that difference. Okay? And we expect these differences to fluctuate from sample to sample, and we've talked about what the variation is going to look like in terms of the standard error. Now, when we construct a confidence interval, we have to understand and appreciate that we are looking at the difference of the means. And in this case, our total focus is on the value 60.72, which is the mean, the sample mean of the males, minus 57.92. So again, after all the smoke clears, and I'm going to try to get this to where on the calculator. All right, so the mean difference is 2.8. So what we do is we come in and we add and subtract margin of error to this, and we get the confidence interval that we get right here. Now let me show you about forms of confidence intervals for the problems that we're working, the two sample problems. Every single confidence interval that you get for a two-sample t-test is going to come in the form of either negative, 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 positive, or positive, positive. Undergrad class, I take a little bit of time to explain that. I think that we all get that. Guys, if we see this form, what you need to understand is that this contains 0. So for this this form, we conclude that the mean difference, and I'm going to go in general here, mu1 minus mu2, is equal to 0. And obviously this will lead to failing to reject the null because there's no evidence to indicate that the mean difference is something other than 0. Now, the other forms, the negative, negative, let's think about that. This tells us that the mean difference is less than 0 because we have two bounds that are negative, which tells us that the first mean is less than the second mean. A form of positive, positive tells us that the mean difference, mu1 minus mu2, is greater than 0. The difference is positive. What we can conclude here is that mu1 minus mu2 is greater than 0. Or I'm sorry, that mu1 is greater than mu2. But guys, in our situation, the confidence interval we have contains 0, so there's not statistically significant evidence to reject the claim that the difference is equal to 0 because our confidence interval contains 0. Alright gang, let's do this the easy way. We've seen the answers, and we can now go into R and show you how you can do this with just using R. So guys, to construct a t-test, a two-sample t-test, we'll go t-test. And then we need our y value, which is read tilde gender. The next thing we need is variance equal. Let's see, we did not do equal variances. And then, for reasons I'll explain in our next video, actually your next video is going to be a link to YouTube that I want you to look at. But paired is false. We're not doing a paired t-test. We're doing an independent samples t-test. And guys, when you get this, you're going to see a lot of numbers, kinda. Now let me explain the difference. What they've done here is they've kind of made an arbitrary choice that they're going to look at the difference from female to male. So their t-value is negative because their sample mean difference was negative. We looked at the difference mu sub m minus mu sub f. They looked at mu sub f minus mu sub mu. So they just looked at the difference. So their sample mean difference was negative 2.8, where ours was positive 2.8. Not a big deal. Degrees of freedom are the same. Your p-value is the same. But, and again, this shows that we tested a not equal to. But guys, notice that your 95% confidence interval is switched. Nevertheless, same thing applies, that we have a form of negative to positive. And so, you know, it contains 0, and, you know, life is good, right? I just want to go back and just double check that we did get that confidence interval. Yeah, we did. Okay. All right. Now, what could we do if we could conclude that we do have equal variances? Well, the t-test that we would run would be very similar. But in this situation, we would do variance equal true. And we're still paired equal false. Now, in this situation, notice that the t-value, the test statistic is a little bit different. I'll explain that in just a second. Notice that the degrees of freedom are much simpler. They're not a decimal, but they're much larger, which gives us more power. And the p-value is slightly smaller than the p-value here. Again, that's all tied back into we're dealing with the different degrees of freedom. Means not equal to 0. Notice that our 95% confidence interval still contains 0. Now, let me go back over and to the blackboard and explain what happens. If we are absolutely, positively, without question, certain that the variances are equal in each of the populations. So for our problem, if we were absolutely, positively certain that the variances for reading score for males was the same as the variance for reading scores for females, then we would be free to run what's called a pooled two-sample t-test. Guys, we cannot run this pooled two-sample t-test unless we are absolutely, positively certain that the equal variance assumption is satisfied. I didn't feel comfortable if this was something other than just an academic exercise, an academic illustration. I wouldn't feel comfortable running a pooled t-test in this situation just because the sample standard deviations were quite different. Nevertheless, if there was some underlying theory, if we knew from previous research that the population standard deviations, hence variances, are equal, then we could run a pooled t-test. Guys, turns out to be the same. We still use the mean difference. Use the sample mean difference to estimate the population mean difference. But what happens when we are able to assume equal variances? We are able to combine the measures. And we do this with what's called a pooled standard deviation. And the notation for the pooled standard deviation is S sub p. Now, let me show you what this is. It's really simple. If we looked at the pooled variance in, I'll tell you what, let me just call this SP squared. So guys, this is the variance, just in case the Kentucky accent is too much for you northerners. So the formula, see if I can remember this. I love to teach without preparing. It seems like my lectures go wacky when I actually start trying to prepare. Although once we get into the tough stuff, I better prepare. It'll be a nightmare. Okay, so the pooled within variance looks like this, and obviously the standard deviation is just the square root of what we get here. So you can think about this as kind of a common variance, and kind of a way of combining. So where do we go next? Next thing we need to examine is the standard error. And the same thing happens, is that the difference in the variances is just the sum. So what we get into here, if we want the standard deviation, which is called the standard error, it's just going to be the square root of SP squared over N2. It should be equal to which clearly is equal to this. All right, so guys, you've got the parts, the pieces of the puzzle here. So you know what changes. Remember your, after you set up your null and alternative hypothesis and select your appropriate alpha. What's in the numerator isn't going to change. Still the point estimate. But what will happen in the denominator is we use this expression instead of the one we did for the unpooled. And again, guys, what's going on here is I'm illustrating a pooled t-test. And the reason I'll spend a little bit extra time on this is we use this once we get into ANOVA. Okay? It should become pretty clear that p-values are still calculated the same way, but in the pooled t-test, the degrees of freedom are much, much, much easier to find. So it's just the sum of the sample size. Okay, sum of the sample sizes minus 2. So we would have, what was it, 18 and 12. So we would have a test degrees of freedom equal to 28. Now, our 95% confidence interval, therefore, would look like this. So guys, I'm going to leave that as an exercise, and you can crunch the numbers and make sure that they equal what we got earlier in R. Guys, that's about all I got. One thing I do want to point out, let's go back to this this equal variance assumption, and this is kind of an interesting point that will either drive you crazy, possibly make you lose all faith whatsoever in statistics. There's actually a test, a technique by which we can test equal variances. And students all the time ask me, well, when constructing a two-sample t-test, when you're trying to determine whether to pool or not to pool, why don't you just construct one of these? Before doing this, why don't you just test this to see if you have equal variances? Well, it's kind of a catch-22 here, in that we're constructing a test of hypothesis with the difference of means, but we'd be using a test of hypothesis that we really don't even trust. Yet we're using a test of hypothesis which we're supposed to trust. Okay, it's kind of crazy, right? Let's think it through. What would happen if, in this situation right here, what would happen if we rejected the null? So let's first of all think about our decision of reject. Well, we draw a line through this and we would assume that population variances aren't equal, so what we would do a unpooled test. All right, fair enough. What would happen if we failed to reject? Fail to reject, so there's more evidence for the null, right? But it doesn't say the null is true. It just says based on the results from the test, we can't reject that statement. So it kind of gets back into a catch-22. What's the focus of the test of hypothesis? To see if there's evidence to reject the null. It's not to make a strong statement of truth or not truth, accept, not accept, true, false, all those strong words. That's not the intent. The intent is there enough evidence to reject the null? And if we fail to reject, there's not enough evidence to reject this. Doesn't mean it's true. Doesn't mean it's false. It just means we can't reject this. So guys, at the end of the day, a test of hypothesis of equal variances actually does us no good, considering that we must absolutely positively for certain know that the variances of the populations are equal before we could run a pooled t-test. So guys, at the end of the day, what's my opinion? Never pool. It's just not worth it. The consequences are just too high. All right, gang, that's all I got. Again, this video is going to be posted. There will be another video. It's really short that I'll post a YouTube link to. The next video that we're going to get into is going to be ANOVA. And I'll probably follow that up with just a short video on dependent samples t-test. I just want you to be aware that when the independence assumption is violated, that we have to take special precautions. So, guys, have a good one.